Okay, so we are going to be talking about synthetic division, which is the second part of 4.3. Synthetic division is a lot simpler than long division, and it doesn't take as much room or time to do it, but we can only use it when we're dividing by binomial in the form x minus h. So I'm just going to explain it using the first example. We see here that we're dividing by x minus 5. That is written in the form x minus h, so we can use synthetic division for this one. The first thing you want to do is we want to focus on only the numbers when using synthetic division. So I am going to pull out the coefficients of the first polynomial. So my coefficient is the number in front of the variable. So I have a 3 here. I have a negative 14, and I have a negative 5. These are the numbers that I'm going to be using when doing synthetic division. And I want to pull out my h value. Now, it's x minus h. So that means that my h is just the 5, not negative 5, just the 5. So when I write this out as synthetic division, I am going to do the 5. Now, my little house is going to look a little bit different. It's going to look like this. Here is my 5 on the outside, and then I want room for 2 lines to go here. In the first line, I am going to write my coefficients. 3, negative 14, and negative 5. You are writing the coefficients to your dividend polynomial. Now, when we do this, we drop the first one down. So that's 3. Now we're going to be moving in a bit of a zigzag here. The first one gets dropped, so now I multiply 5 times 3. So 5 times 3, here's a little dot for multiplication, equals right here. And that is going to equal 15. Once I'm here, I am going to add. Negative 14 plus 15 gives me a positive 1. Now, I am going to keep my signs always, and I'll show you why at the end. So just get used to always writing your sign with it. For the next one, I am going to follow that same step that I did here, but now I'm going to do it with this one. So I'm going to multiply that 5 times positive 1 and write what it equals in here. So 5 times positive 1 gives me a positive 5. And now I'm going to add again. Negative 5 plus positive 5 gives me 0. So now I am left with 3 plus 1 and 0. Now in this part, these become my coefficients to my quotient. I have a 3 and I have a plus 1. The only thing missing here is my variable. I'm going to drop one variable because I'm dividing by it, so I'm pulling one out. Since I'm pulling one out of 2, I am left with just 1. And that becomes my quotient. Now, if I were to show you the one we did with long division, you notice that I did the same problem. I divided the same divisor by the same dividend by the same divisor and got the same answer here. So it doesn't matter which method you use, you should have the same answer. It's just that most people prefer doing this in comparison to this. So let's start another example. Okay, so in this example, I'm going to start off the same way. I'm going to pull out all of my coefficients. Here I have a 1, positive 7, positive 11, negative 4, and I need to find what that h value is. So here says x minus h, but here I have x plus 4. So if you remember back in transformations, we talked about taking the opposite. It's the same case here. This is a negative, this is a positive, so we would have our h be -4. So now I'm going to set up my little house again. So -4, remember you want to leave room for 2 lines and make it long enough for all of your coefficients. So 1, +7, +11, and -4. We drop our first one. -4 times 1 gives us -4. Now we add here. 7 plus -4 gives me 3. Now I multiply -4 times 3, and that gives me -12, which I am going to add. 11 plus -12 gives me -1. I'm going to multiply -4 times -1, and that gives me a +4 here. -4 plus a +4 gives me 0. So now these become my coefficients. So 1, I forgot my plus here, +3 -1. Now remember I said I would explain why I like to keep that, because when I move this over, it's easier for me to know it's 3x plus 1, and then I don't forget that sign. So next I drop one of the variables, so this is x cubed. I would have x squared plus 3x minus 1. And that's it. This number here is our remainder. So you could see that I don't have a remainder. I'm sorry. There we go. We don't have a remainder when we did these first two. You may have noticed that these look a little bit familiar, and that's because they are the ones I did in the last video when I solved using long division. So you notice that I said there's no denominators yet. Same thing. So what would something with a remainder look like? Okay. So you notice I changed the color. The first thing I want to do again is write out my coefficients. So I have a -1. I have a +4. But wait, I have a 3, a 2. I am missing the 1 before I get to the 0. So I am going to add that. Just like we did with long division, you need a placeholder. You need every variable to be there, represented in some way, even if it's just with the 0, but you need to represent it. My value of h is 3. Remember, you take the opposite. So now when I set this up, I get -1, +4, 0, and +9. Now, when I first did this problem on my own, I thought I did something wrong because I was just used to having a 0 as a remainder. So I went back and I checked, and then I checked to make sure I wrote the right problem down. But it was right. It just so happens that now instead of having a remainder of 0, I get a remainder of 18. So when I write this, -1 plus 1 plus 3 plus 18, I drop one of the variables. to x. And this 18, that is our remainder, will go over our divisor of x minus 3. And that becomes our solution. This is synthetic division. We pull out the coefficients, making sure every one is represented, even if it's by a 0. Our h is that opposite of the inside, which goes out. We drop the first one. We multiply that by this and put it there for each single one. So it's easier to see on the first one because I drew the arrows. We're going to do 5 times 3, and it goes under the second term. We add those two. Then we multiply that by whatever that sum was and put it here, and we repeat the process. So we add whatever we got there. We would continue just like we did with all the others. Another helpful way to use synthetic division is to evaluate. So let's look at an example for that. Okay, so before I start using it with synthetic division, I want to do it the way we have been doing it in the past, just so I know that I get the right answer. Since I'm given a value for x, I'm going to substitute every x value with that and solve. Okay, here we go. I plugged it in. I got 3 cubed is 27, bring down the negative. 3 squared is 9, times 4 is 36, bring down my 9. So I ended up with 9 plus 9, which was 18. So I know that my answer has to be 18. You may also notice that this is the same problem that I solved up here. Now, the remainder theorem tells us that when we divide using synthetic division, or long division would work as well, if a polynomial f of x is divided by x minus k, which in this case we used h, the remainder is that f of that. So whatever I get when I plug in this number would be the same thing as my remainder when I divide by that. So here, I plugged in the 3 and got 18. But when I used the synthetic division, I also said that that value was 3, and that is what I used in this method. So if the remainder theorem is true, that means that whatever my remainder is when I use synthetic division should be the same thing as when I plug in that number, which in this case is true. So when you're asked to evaluate something, you can do it this way, which is what we've been doing, or you can use that number to set up your synthetic division, and your remainder would be the answer as well. In this case, plugging in 3 wasn't that big of a deal because it was pretty straightforward. But if you had something that was a bigger number, you might want to do something like this. Let's look at this problem here. So one way you can go about this is plug it in. So then you would be doing -4 to the power of 4 and then multiplying it by -3. And then plugging it in here, cubing it, and then multiplying whatever you get there by -13, and then continuing the process. Some of you guys might not mind doing that, but if I'm being honest, I don't want to do it that way. So I'm going to use synthetic division to solve for this. I'm going to write out my coefficients, making sure that every variable is represented, and I can see that it is. -13, -8, -12, and then plus 23. And I know that I'm going to use -4. So when I set this up, I get -4, -3, -13, -8, -12, plus 23. Make sure that that's long enough. I'm going to bring this one down. -4 times -3 is a positive 12. I get -1. -4 times -1 is a positive 4. -8 plus 4 is a -4. Multiply that out, I get a positive 16, which gives me a positive 4. That would give me a negative 16, and that gives me a 7. Since for this, I only care about what that value is, I'm only going to focus on that remainder, which is 7. So I know that when x is equal to negative 4, so f of negative 4, I get 7. And like I said, this is called your remainder theorem. If you want to test me, you could go ahead and plug that into that and then solve and see if you get the 7. I'm not going to do it because I trust the remainder theorem, but you are more than welcome to do so. That's it. So just a quick recap, you can use synthetic division to divide when you have the divisor being in this form, x minus h. You take out the coefficients, you take the opposite of that, set it up. Remember that you drop the first one, you multiply, and you plug it in to add it with the second one, so on and so forth. Keeping in mind that you need a placeholder so that every variable is represented. You could also use synthetic division and the remainder theorem to find what a value is at a given x.